Hi all, thank you for joining. I'll be presenting analyzing differentiable fuzzy implications. This is joint work with Erman.
To yourself. Okay, sorry, I was supposed to present you, but okay. Okay, yeah, this is a paper analyzing differentiable fuzzy implications by Emile van Krieken, Erman, Acar, and Harmelen. Okay, so the speaker is Emile. Please go ahead.
Thank you. Sorry. Well, let's get started. You already heard the title, so we don't need to repeat that. We read at Kr plus Ml. In both of these approaches, we have different ways to represent knowledge. In deep learning, in neural networks, we present knowledge and semantics using high-valued vector spaces. The semantics is hidden somewhere in there. It is difficult to interpret this or extract it. In Kr, we are dealing with symbolic knowledge. It is easy to interpret, it's generalizable, it's extensible, but it's brittle to noise and exceptions in data. So both these representations have their own benefits. So the question here is, can we get these representations to interact and get the best of both worlds? One way would be to say, well, we have all this domain knowledge, all this common sense knowledge, all this knowledge that we've written in our knowledge representation format. And can we try to incorporate this knowledge, inject this knowledge into our deep learning representation? That would be quite useful. The other way around is also interesting. It relates to the symbol grounding problem, which is introduced by Stephen Harnett in 1990. He says, how can a semantic interpretation of a symbol be made intrinsic rather than just parasitic on the meanings in our heads? Symbols that we use to reason with in computers have a meaning to us because we know what they refer to in the real world, but they are not really connected to the real world for computers. A unicorn, you know, every computer can reason with the knowledge it has about unicorn, but it never really knows what these symbols refer to. However, the representations in deep learning are connected to the real world through data. This data comes from the real world in the form of images, text, or sound, which relates it to the real world and connects it to the real world. The idea is that we can use neural networks to ground symbols, to connect them to the real world. This allows us to use knowledge representation settings, knowledge representation methods and settings where we also need to connect to the real world. Differentiable fuzzy logics is a broad range of methods that do this. So basically, in a deep learning, they use deep learning to interpret symbols, and I have a knowledge base written in fuzzy logic that is used to correct inconsistencies and correct the deep learning system using the backward knowledge. In differential fuzzy logics, like in fuzzy logics, we have truth values, which are numbers between 0 and 1. Connectives like conjunction, disjunction, and implication are differentiable operators on these truth values. We will be focusing on fuzzy implications, of which you will see some well-known examples on the right. In the forward pass of our system, we will interpret symbols in our differential fuzzy logics, such as predicate symbols or function symbols, using deep learning. As predicates are, in a sense, just functions of objects to 0, 1 truth values, we can use neural networks to predict these 0, 1 truth values, numbers between 0 and 1 then. The interesting thing is that if we now describe our knowledge base using fuzzy logic, and we compute the truth value with this grounding from the deep learning, we can actually differentiate the truth value that we get from the knowledge base. Because all of the connectives are differentiable, and we can use a chain rule of differentiation to optimize the parameters of a deep learning system. And we will show that in using this, what will happen is that we can use domain knowledge to correct inconsistencies in the predictions of the deep learning system. In this talk, we will focus on the choice of fuzzy implication in such a system. Previous work has already focused on differential fuzzy logics. The most common example maybe is logic tensor networks, which was introduced by Serafini in 2016. Semantic weights regularization is also a common one that is quite similar, but the focus on support vector machines. Neuro-T improver is a more machine learning focused model for knowledge-based embeddings, which uses a Gödel T-norm to reason. Other methods, more recent, also focus on generative modeling like lyrics or other methods. I will argue that a cool application of these differentiable fuzz logics is that we can use it for weakly supervised learning. In contrast to supervised learning, this is a setting where labels are missing or incomplete or noisy. It's more challenging than just having all correct labels. Let me show you how this is done. Let's consider this toy setting where we have a teacher and a robot. The goal of the robot is to predict what objects are and what are the properties of objects. So it sees a blue cloud, and of this cloud, this robot has to say what it is. Now we have a very peculiar teacher that doesn't actually know either what this cloud is. It only knows that ravens are black. Now, if our robot says that the cloud is a white raven, this is not consistent with the background knowledge that our teacher has, because our teacher knows that ravens are black. So the teacher can use this background knowledge to correct the robot. It can use a Modus Ponens rule to say, you saw a raven, so what you saw also has to be black. This is very useful for semi-supervised learning. The teacher does not actually have to know that it is a black raven, but it can use its background knowledge to correct the robot so that the robot is able to learn new things by using our domain knowledge. This is not the whole story, however, because the teacher, although it knows that ravens are black, can make other ways, can correct the robot in different ways. By contraposition, the teacher can also argue that because it did not see a black object, but it saw a white object, it could not have been a raven. This is by contraposition of the implication. Another possibility is to say, well, you might just have found an exception to the rule that we know of. Because the white ravens actually exist in the real world, this is often something that could happen. To show this in a bit more of a practical context, let's consider one of the implications. The Canadian implication is a simple one that says 1 minus a takes a maximum of 1 minus a and c, where 1 minus a is a negated antecedent of the implication, and c is a consequent of the implication. If we now have a robot that predicts 0.9 for raven, the antecedent, 0.3 for the blackness of the object, the consequent, we will use a maximum of the negated antecedent and the consequent, which is 0.3, namely the blackness of the raven. If we now look at the derivatives of the implication, which is what we'll be using when we're optimizing our truth value, then we're going to see how the teacher is going to correct the robot. We are going here to the first case. 1 minus a, the negated consequent, the negated antecedent is smaller than a consequent. So what the teacher says is we're going to increase our consequent. We're going to increase the black by 1. Similarly, if the raven says 0.2 for raven and 0.1 for black, we go to the second case. 1 minus a is now 0.8, the negated antecedent, and the consequent is 0.1. So we're now going to decrease raven by 1. This is the second of the two possible derivatives that are possible here. If we look now at a different implication that we can choose, for example, the Gödel implication, which is actually a common one in many real-valued logics, we'll see that different kinds of reasoning behavior happens. Again, if we take 0.9 and 0.3 for raven and black, we are again going to choose to increase black by 1. Why? This is because if the antecedent is smaller than larger than the consequent, this implication is equal to the consequent. So the derivative with respect to the consequent is going to be 1. However, if we now look at a different setting where the robot says 0.2 for raven and 0.1 for black, we're also going to increase black. Because again, the antecedent is larger than the consequent. So while previously we would do Modus Ponens reasoning and decrease the ravenness of the object, now the teacher is going to correct it by increasing the blackness of the object because it uses different implication. Does it make sense to do it this way? We argue that it is not. Just consider in the real world what we are thinking about. You could say there are about 20 million black ravens in the world. This is just something, the number grabbed up in the air. It's not really relevant if it's actually true. The amount of non-black and non-ravens, however, is infinitely much larger. Well, not infinitely, but hugely much larger. So actually, just looking at the probabilities, just looking at the statistics, it is quite likely that correcting it using Modus Ponens should actually be more accurate. There are also exceptions, which makes designing such knowledge bases very hard. To show this in a simple toy experiment, we'll be looking at a simple MNIST problem, where we are doing semi-supervised learning with 1% labeled data and 99% unlabeled data for our differentiable fuzzy logics. We use a very simple knowledge base that is based on a sameness relation. Namely that if you have two digits that are both zeros, then they represent the same digit. If you have a 0 and you have two digits that represent the same digit, and the other one also has to be 0, and sameness is reflexive. These are very boring rules, but you already show in this very simple problem setting that this is going to happen. Differentiable fuzzy logics, we ground these predicates using neural networks. They're interpreted using neural networks. So for example, 0 to 9 is going to be a convolutional neural network, a classifier of MNIST digits. The rules are used to provide the system with feedback and to correct inconsistent predictions. And we're going to compare some different fuzzy implications. In this, on this slide, you will see some results. For 6 implications, you will see that the performance is actually wildly different. Without using any differentiable fuzzy logics, we get 95.1%. But if we add them, then some of the implications will result in better accuracy. So we make use of the unlabeled data, while by others, we're actually going to get worse accuracy. So for example, the Gödel implication that we saw the second actually decreases the performance. This is because it uses Modus Ponens reasoning too much. We designed a smoothed out implication, which also improves it the most, although the difference isn't that big. You can look at the paper for more information and reasoning behind why some of these implications work better than others, or also what is the reasoning behind how they reason in a sense. We also show in the paper that you need only a limited amount of Modus Ponens reasoning. In fact, if you have too much Modus Ponens reasoning compared to Modus Ponens reasoning, you're going to do worse and going to make more mistakes. This is harmful to your reasoning process and introduces mistakes in your learning. If you would like to know more and see how these fuzzy implications and their derivatives determine the reasoning process and the learning process, you can look at our paper. In an extended paper, we extend this analysis to conjunction, disjunction, and universal quantification. This can be found on arXiv. And also, if you have any questions, please let me know right now.